Well, so thank you very much for the invitation and that very, very generous introduction. I hope to never win the Ig Nobel Prize, but um, okay. So thank you. So what I'm going to talk about today is not what we've learned about binary black holes or the black hole dynamics, but it's to tell you a little bit about what we still don't know about the dynamics of black holes in Einstein's theory of relativity. So this is purely classical. I'm not going to say anything about quantum mechanics. So I want to talk about some open questions about the dynamics of black holes. Now, I've got sort of two of them listed here, and so it's like in the abstract of my talk that I submitted. I said, like, the two things that I'm going to say we don't know very much about right now in classical Einstein gravity is what happens with nonlinear perturbations of so-called near extreme Kerr black holes. So black holes that rotate as fast as we think they're allowed in relativity. And I've also listed here the ultrarelativistic limit of binary black hole interactions. But I think this is too ambitious. So I've given a version of this talk before, and it was rushed to get through in 50 minutes. And so I think just because I won't be able to sort of explain all of this without first telling you a little bit about what we know, getting everyone on the same page. I'm not going to assume that everyone here knows relativity or all of these things about black holes. So I can immediately tell you what we don't know if I don't explain a little bit about what's so interesting about black holes, why their dynamics is so rich, why there's so much, why they're such interesting objects in relativity. So I'm going to be a little bit less ambitious about what I can get to. So I'll probably spend about the first 2/3 of this talk. It will be some introduction about general relativity, about gravitational waves, in particular about the dynamical strong field regime of general relativity, to try to tell you a little bit about what that is compared to weak field gravity. And then I'll be able to explain what I mean by this problem in more detail. And I probably won't have time to get to this, but I'd be happy to afterwards if people want to talk to me about this ultrarelativistic limit. I'd be happy to talk about that. Okay, so what's the motivation? Like, why am I interested in this? And this is basically just to understand in all of its rich, intricate details what a black hole is in Einstein's theory of relativity. So from the most basic perspective, if you want to say, okay, general relativity is a theory of gravity. So you might think the simplest thing to think of a black hole, it's the analog of a point source in Newtonian gravity. Well, what is a point source? A rich, intricate object with lots of interesting dynamics in Newtonian gravity? No, it's completely trivial. It's just a point source. You don't need more than a few seconds to explain what you mean. But so a black hole is kind of, in a certain sense, you can think of the simplest gravitating structure you get in Einstein's theory if you had a hypothetical point source of matter. But the structure of a black hole spacetime is incredibly rich. So even before we get to binary black holes, even a single black hole, it's an incredibly rich object in Einstein's theory. And even today, 100 years plus after Einstein proposed the theory, there's some things just theoretically we don't understand about the dynamics of black holes. Okay, so let's start from the very basics, just to get us all on the same page. So let me just give you some, especially for those of you that aren't familiar with general relativity, I'll just give you some of the, hopefully like a flavor of it so that you can sort of understand some of the things that I'll say later. So of course, it's Einstein's theory of gravity. But the thing that's philosophically so interesting about it, it's really not a theory about a force. It's really a theory about the nature of space and time. And Einstein's theory posits firstly that space and time can mathematically be represented as a four-dimensional geometry. And geometry, if you think, well, what is the easiest way perhaps to understand geometry is essentially just Pythagoras' theorem. So for example, if I said we have a flat Euclidean geometry, what does that mean? Well, it means that any 2 points that you pick, you can describe the distance, the shortest distance between them by Pythagoras' theorem, the sum of the squares, square root, etc., that formula. And so that's, if you feel, that's a definition of Euclidean geometry. So Einstein says that, well, space and time that we live in is a geometry like that, except for a couple of important differences. One is, well, it's now space and time. We can't separate them cleanly, so we have to have a four-dimensional geometry. But also that geometry can be varied over space. It can be varied in time. It can be dynamical. So we can still describe it with something like Pythagoras' theorem, but we don't want to use that the formula between distant points, we want to use an infinitesimal version. And that's what I've written here. So this is essentially just an infinitesimal version of Pythagoras' theorem, saying that if you have say a point, and you have some point that's infinitesimally separated from it by now these little differential distances, this says that the distance squared between those 2 points is given by this generic quadratic form. So, this is like we're summing over all of the indices. So xa, x1, 2, 3, 4 can be t, x, y, z. So it's the sum of the squares of the distances. And you'll see in a second why we don't take the square root in general relativity. But that's really one of the first fundamental postulates of general relativity, is that space-time has a geometric structure that can be represented in this infinitesimal Pythagorean form. Okay, but of course, if space-time can be dynamical, it can have structure, where does that structure come from? What governs it? So the other part of Einstein's equations, and this was where the real difficulty comes in, is it does have equations, differential equations, that tell you how space-time comes, or what are allowable geometries and how they evolve. And that's given by sort of the famous Einstein equations written in this very deceptively simple tensorial form. So this is something called the Einstein tensor, which characterizes some function of the metric that I mentioned on the previous slide, this little Pythagorean thing. So if we want to understand space-time, we need to know this little metric tensor. So this is this, you can think of this as a matrix, a 4x4 matrix of functions that describes all the little infinitesimal distances. So if we know this, we can answer any question about space and time. So from this object, you construct another tensor called the Einstein tensor. It's also, you can think of it as a 4x4 matrix. It's symmetric of functions, and that characterizes geometry. And so what Einstein's equations say is that this particular object that you build from the metric isn't arbitrary, but it is constrained by the matter content in the space-time. So this TAV is a stress energy tensor of matter. So that includes energy densities, pressures, momentum densities, and it has to satisfy this relationship. Here, G is Newton's constant, C is the speed of light. Okay, let me just, before I explain what I wrote down in words below, so okay, this is the theory of space and time. It's a theory of geometry. Well, where does gravity come into this? Well, of course, people know that the fascinating thing about this, if you posit this, you don't need a force of gravity anymore to explain what we see and experience as gravitational phenomena. So for example, if you solve this equation, say for conditions around the Earth, what it will tell you is that the Earth, it sits here on the right-hand side. There's a lot of energy, there's a lot of mass in the Earth. So this equation says that the Earth produces a curved geometry. Now we also have matter, we also curving geometry, but relative to the Earth, we're insignificant. So we essentially little test particles in the geometry. And you can say it's an hypothesis, but it's actually a consequence of the Einstein equations, is that little test particles follow geodesics through the space-time. So geodesics are curves that extremize distance, or it will minimize, it's the optimal path through space-time. And you say, well, what is the geodesic of one of us here in the curved geometry produced by the Earth? And these are free fall trajectories. So these are trajectories where we want to fall straight towards the center of the Earth. So that's, in Einstein's theory, that is a trajectory where there's nothing acting on you. There's no force acting on you. So in Einstein's theory, there's no force of gravity that's pulling us to the Earth. It's actually the opposite. Our natural force-free path is following towards the Earth. And it's the other forces, like in your chairs and on the ground, that are preventing us from following these geodesics. And to a very high degree of accuracy, that is equivalent to Newton's laws here on Earth. Of course, there are other effects, and relativity is more consistent than Newton's theory, so it's the better hypothesis in that sense. But it's kind of remarkable that a completely different framework can explain a force. It's a curved geometry versus an actual Newtonian force. Okay, but how would you go about solving the equations? What do they look like? And of course, I'm not going to show them, but I'll just mention. So if you take this thing and you construct this Einstein tensor, what you find is that you get a set of 10 second-order nonlinear partial differential equations for the metric, the 10 independent components of the metric. Again, it's a 4x4 matrix of functions, but it's symmetric, so they're 10 independent functions. And so we want to solve those partial differential equations to get the metric that I showed on the previous slide and then we can understand everything about the space-time and interpret then things like the orbits and whatever, gravitational forces, etc. Okay, so for example, one solution, and this is, if you will, the simplest generalization of Pythagoras' theorem, is like, what is a four-dimensional space-time which is completely flat? And one of the solutions is Minkowski space-time, which I've written here. And so this is, if you will, this is the space-time of special relativity. So special relativity you can also think of as a theory of space-time. But in special relativity, space-time is not dynamical. It's just given by this, and that's what it is, at least in this coordinate system. So one interesting thing here that I mentioned before, like why we don't take square roots, is this is the distance squared. This is the usual Euclidean piece, but time adds in with a minus sign. So distance squared can be positive, negative, or zero, and that's very important in Einstein's theory to have that. That essentially allows you to describe causality. But of course, then the other thing is, like, this equation wouldn't make sense if this was just t, dt squared. We need something of dimension velocity to make this dimensionally consistent. Everything has to be length. And so, in this sense, this is just a constant, but it turns out to be a constant. The constant is the speed of light. Then it matches observations. Okay, so if I say, like, this is a theory in vacuum, and then you say, well, okay, is that the only vacuum solution? But the thing that's going to play a key role in what I'm saying about, like, the interesting things in Einstein's equations is that this object here is a very nonlinear function of the metric tensor. And so there is no simple uniqueness that you would get for linear equations. And even in vacuum, you can have many other solutions other than the Minkowski metric. And in particular, for this talk, the interesting solutions that you can get in pure vacuum. So there's nothing like what you think the Earth is producing curvature. Or another way of thinking is that curvature can itself produce curvature because of the nonlinearities. And what can happen then is you can get solutions such as black holes and gravitational waves. Of course, they can exist if there's matter, but the simplest representation is as vacuum solutions to the Einstein equations. Okay, so let me, to get to the strong field regime of relativity, let me first explain the weak field nature of gravity. So first, let's look at the weak field nature of gravitational waves. So this is looking at the vacuum equations, and let's take little perturbations of Minkowski spacetime, and you find that one kind of solution you get waves that propagate at the speed of light, if you will, little ripples in the geometry that propagate at the speed of light. And so I've written the perturbation for one, so you get this to linear order, so we're not taking the nonlinear effects into account. So to linear order, we're taking a small perturbation, so we can write that metric as the Minkowski metric that I had on the previous page, plus a perturbation. And this is an example of a solution that you get to the linearized equations. So what you find is that there are two linearly independent polarizations. So this is much like Maxwell's equations. If you get radiative solutions, you get two polarizations. It's also this case in Einstein gravity that there are two polarizations. And what the polarizations physically represent, so you can think of, like in this case, I've got a wave that's propagating in the z direction. Both of the polarizations are transverse, so they produce distortions in space and time, but only transverse to the direction of propagation. So if it's traveling in the z direction, it's only going to distort space in the x and y direction. And so that's what this represents here, is that the perturbation only has these components in the x and y direction. They're two linearly independent polarizations. Okay, and you can see here they propagate at the speed of light. So it's some arbitrary function of t minus z over c. So this is a wave propagating the positive z direction at the speed of light. This is a so-called plus polarization. This is the cross polarization. And okay, you can, if you mentally can do the mathematics of how this is changing distances, it's just easier to just look at a picture. And you've probably all seen this picture before. Like what physically does it do to distances? And so this is what the two polarizations do. So you imagine, let those h plus and h cross functions be just sinusoids. So again, it's a wave propagating in the z direction. So in this case, it's propagating right into the projector. So this is our x and y and z's into the board. And you'll find, so if you take like a circle of particles and say, so this is now again metric, it's distances. So the wave is passing, so it's changing distances. This plus polarization is going to, in this oscillatory fashion, will stretch and squeeze distances along x and y. So if it's a sinusoidal wave, it's going to stretch and squeeze distances like this. The cross polarization is qualitatively exactly the same, but it's rotated at 45 degrees relative to the plus. So a general perturbation that's in the z direction is some arbitrary sum of the plus and the cross polarization. So that's what you get from solving for small perturbations about Minkowski space, the Einstein equations to linear order. Okay, so for these waves, like very analogous to electromagnetic waves, this is a classical theory after all. So you say, well, do these waves carry energy? Yes, they do, but it's not TAB, stress energy, like material energy, but it's like in Einstein's theory, all forms of energy gravitate, including space-time itself. And so these waves do carry energy. And in this weak field limit, you can actually calculate that. And it says that the flux of energy is equal, so there's a little technicality about doing some appropriate time averaging, well, that's what this bracket means, but just qualitatively, or that'd be more quantitatively, but what's more relevant here is the sum of the squares of the amplitudes of the time derivatives of the perturbation. So this is very much like electromagnetism, like the Poynting flux is E squared plus B squared. Here it's H plus dot squared plus H cross dot squared. So it's positive definite. The interesting thing here also that I want to highlight is the dimension for constants that multiply these volumetric perturbations. So again, the speed of light is there, c, this is g. That's a very large number. That's a very small number. So this is a very, very large number. And so what it tells you in some sense is space-time is very, very stiff in terms of energy content. So if you had a mechanism of feeding energy to perturb space-time, you'd have to have a tremendous amount of energy to even have a small noticeable perturbation, right? So, or said another way, I mean, gravitational waves are, this is creating gravitational waves. Like why we don't feel it is this energy is insignificant. And so the amount of H plus and H cross to give a certain energy is incredibly small because of that factor. Okay, so again, how do you produce gravitational waves? So that was, okay, there's a gravitational wave that propagates at the speed of light. How do you produce it? Well, again, at linear theory, we get, so the leading order description is this famous quadrupole formula that Einstein even derived in 1960. And basically it says that the leading order description is you need a dynamical source, you need motion of matter energy. And here in this limit, you just think of actual matter. So if you take stress, you take matter, the TAB part, but it could even be like two black holes or vacuum solutions. But what you need is you need an asymmetric acceleration of matter to produce gravitational waves. So here we imagine we have a little source, it's oscillating in some fashion, and it's going to be producing gravitational waves. And at some distance r, we measure this little perturbation. And so this quadrupole formula says that the waves that we measure, first of all, they decay like 1 over the distance from the source. They travel at the speed of light. And it's proportional to the second time derivative of this so-called trace-reduced quadrupole moment of the matter. So it's just taking the energy density, like the monopole moment would be the integrated energy density. A dipole moment would be the integral of x times rho. So what this says is that monopole oscillations, or spherically symmetric oscillations, don't produce gravitational waves. Dipole oscillations don't. You need the first leading order kind of structure you need is a time-varying quadrupole moment. So this double dot is a second time derivative. So you need an accelerating quadrupole moment to produce gravitational waves to leading order. But then again, the other interesting thing, getting back to this question, like how stiff space-time is again, we have these constants here. They appear in the reverse fashion, but g over c to the fourth. And again, now this is an incredibly small number. So again, this says like, okay, if we want to produce a noticeable amount of perturbation in space-time, this is such a small factor, we have to get this to be very, very, very large. So we either need incredible energy densities or incredible accelerations. And so that's why, yeah, I'm producing gravitational waves, but no one has ever done in principle, like E and M, you can have a gravitational wave emitter and a receiver. So we could communicate by gravitational waves like we do with radio waves, but it's completely impractical here because of the energies involved. And so that's why the first gravitational waves, the direct detection was, with incredibly sensitive instruments, and you've probably heard talks about LIGO and the incredible sensitivity that they've achieved. So they had to get incredibly sensitive detectors, but also we had to look to the universe to give us conditions where we had incredible densities and incredible accelerations. In particular, the most dense that we can make things in relativity, that's black holes. And when they collided, well, they were traveling at close to the speed of light, well, 30, 40% the speed of light, incredible accelerations. Okay, so this is the weak field nature of gravitational waves. And okay, this is, even though most of my talk, especially with the stuff we don't know, is going to be mostly of theoretical interest. As scientists, it's not interesting in some sense if it doesn't describe reality. So is this description that Einstein theory predict consistent with reality? And for at least about 30 years now, we've had very good evidence that this weak field nature of gravitational waves is correct. And this is from the famous Hulse-Taylor binary pulsar. And this was a sort of an update that they did several years. They was discovered in the 70s. Yeah, I guess they got the Nobel Prize in the 90s for this one. But so in any case, so this is a pulsar in a binary. So a pulsar is a compact neutron star with a magnetosphere that emits pulses, and they can time those pulses incredibly accurately. And so over many years, they found that the orbit of this pulsar is decaying. And so this is sort of the measurement of, again, the shift of the periastron time of the pulsar. But in any case, because it's such an accurate clock, essentially, they could measure that at the rate of change of the decay of this orbit. And so what's happening in Einstein's theory is that these two the bodies are orbiting each other. They're producing gravitational waves. And as I showed you before, gravitational waves carry energy. So if this system is losing energy, it's got to come from somewhere. And you can use Newtonian intuition. It comes from potential energy. So if it's losing energy, it's got to gain potential energy, but potential energy is negative, so it gets more tightly bound. And so that's why in relativity, orbits are unstable. They're unstable to the emission of gravitational waves. And this is the measurement. And this line is not a fit to the data. It's a prediction from the quadrupole formula that I showed before. So I mean, when I first saw this in grad school, it was like astonishing that there's a theory where it predicts something, so astonishingly accurately. So this is very good evidence that at least the weak field description of space-time as given by Einstein is correct. Okay, but we want to get to the things we don't know, and the things we don't know are the nonlinear regime. So what's strong field? In particular, there's one thing that's kind of interesting about the field equation. It's a little bit puzzling. If we think of other fundamental forces that we know, when there's some qualitatively new behavior that shows up, it's usually because some length scale or some energy scale is crossed. Like in QED, there's the mass of the electrons. If you have a strong enough electric field, you can pair create, but it's because of the various scales in the problem. Like weak fields don't just pair create. So they're specific scales where if you cross them, you can see new phenomena. In Einstein's theory, there's no scale in the problem. Okay, there's G and C, but those are, from a geometric perspective, there are no parameters of dimension length in the theory. It's a scale-free theory. So why would there be a strong field regime? Why would a strong gravitational wave just be able to have a larger amplitude? Why is there something different? And the surprising thing is it is a strong field regime in relativity, which is qualitatively different from the weak field. And it comes not from some intrinsic scale in the equations, but because of the nonlinearities in the equations. And it's actually very difficult to, paradoxically, not easy or impossible to actually characterize it in a very sort of a very qualitative sense because of various properties of general relativity. But at least in a couple of cases, we can sort of get an idea of how do we get to the strong field regime? And one is if we have in like roughly spherical concentrations of matter. It doesn't have to be exactly spherical. That's why I've drawn. So imagine a bunch of matter, this little puffy thing. So it doesn't have to be spherical, but it's got to be sort of in a topologically spherical if you want. So if we take a certain amount of matter, say the total mass is m, and here in Einstein's theory, it actually doesn't, again, anything that produces energy is fine. So it could even be gravitational waves, but let's just think of matter. So it would be matter or energy, which mc squared would be the equivalent. And from this object, you compute this quantity called the Schwarzschild radius, okay, hinting at where we're going. But so this is just taking this mass and just converting it to a length scale by multiplying by 2g over c squared. And so we say, so this object is going to have a radius. You know, this is this hoop conjecture. It's like the biggest hoop of radius R that can completely enclose the matter. And you say, compare that radius to this quantity that you computed, the Schwarzschild radius. If this is larger than that, and quite a bit larger, we're in the weak field. If it's a lot less than that, we're in the strong field. So you can either get to that by compressing this thing into its Schwarzschild radius, or just increasing its mass such that the Schwarzschild radius is larger than the object. And that's when we get this transition to qualitatively new behavior. And so what happens? Let's take this like object, say we do that with the Earth. And so if you will, like for the Earth, if we had to make it strong field, we'd have to compress it down to about 1 centimeter in radius. So we're very, very, very weak field here on the Earth. But if you could do that, then remarkably, the nature of space-time changes completely. So in principle, you could have like, the Earth is approximately stationary. But when you get to that regime, space-time in some sense breaks. It becomes intrinsically dynamical. Interior to that Schwarzschild radius, space and time starts to flow towards a singularity, a geometric singularity. And then other remarkable things happen outside it, but near this region. In particular, you know, there's the time dilation, gravitational time dilation effect in relativity. So if you're close to a strong gravitating body and you measure your local rate of how fast your local watch changes relative to a distant observer, it will appear to be a bit slower from a distant observer's perspective. Now, when this gravitational collapse happens, that time dilation gets more and more extreme, such that when you get close to this collapsing region, it goes to infinity. So you get infinite time dilation. And again, there's a lot of other interesting things that happen, but basically everything that I've described here is a black hole forms. So if you cross this threshold, and again, there's no intrinsic scale. This can happen at any length scale in the theory. At least if that condition is satisfied, then space-time breaks and you form a black hole. I mean, break colloquially, but yes, these things happen, and that demarks the strong field. And interestingly, there's also a dynamical part of strong field. So if we went back to the perturbation theory stuff that I mentioned, that's in perturbation theory. So you say, okay, well, what happens if you make the perturbation large? And relative to the other scales, like what if that H becomes of order unity in proper per units? And so in the end, it's like, well, what if you have some really, really rapidly radiating system? And interestingly, what you'll find that you'll reach the strong field regime in the sense that the amount of energy in the gravitational wave produces will cross that hoop conjecture threshold. So if you could radiate sufficiently fast, you'll produce so much gravitational waves that it will cause a black hole to form. And you say, well, when does that happen? And that's when the radiation approaches the Planck luminosity. And what's interesting about this is, you usually think about Planck stuff as being associated with quantum effects, but Planck luminosity doesn't have any H bar in it. So this really is and it's interesting that there's a classical limiting magnitude, which somehow, it seems like relativity somehow knows about quantum gravity, but this is just pure classical gravity. So if you could develop a system that could produce radiation at the Planck luminosity, the conjecture is it would just form a black hole. Okay, so this is sort of the weak and the strong field. I said like one of the most interesting things about strong field gravity is that then black hole form. So what do we know about these things? What do we know about black hole solutions of dynamics? And essentially what I've described in the last 30, 40 minutes is essentially what was discovered in what was called, I think Kip Thorne named this the golden age of general relativity in the 60s and 70s. And this was kind of a revolution, first sort of on the theoretical front, where people finally started to understand these properties of black holes, really understanding what these solutions were. The singularity theorems of Penrose, I guess he won the Nobel Prize for this a couple of years ago. This the uniqueness properties of the no-hair theorems. It's remarkable that we have an analytic solution for the most general black hole solution that general relativity allows, this rotating Kerr solution. And, there's also a whole bunch of quantum effects, which I'm not going to say anything about. But at the same time as people were sort of understanding black holes from a theoretical perspective, there were hints from the universe that perhaps this actually wasn't just some interesting corner of theory space, but it was relevant to actual objects in the universe. And in particular, the first hints that stellar mass black holes could exist was, these stellar mass, these binary stellar X-ray systems, which hinted at a black hole, or supermassive black holes, sort of at the centers of what we think of as most galaxies. There was evidence that, well, there wasn't evidence that they were black holes, but it was difficult to explain what astronomers were seeing if they weren't black holes. And again, well, it's interesting if that's happening, but is Einstein's picture really a good description of it? Is that bizarre thing of space-time breaking and forming horizons really what's happening? And there's, even I think for 20, 30 years now, there's been developing evidence, and I think I would say there was, before LIGO, I said there was almost incontrovertible circumstantial evidence that there are objects in the universe that are at least compatible with black holes. And that's, again, that was also, as part of Penrose, when Penrose got the award, it's also Gensler and Ghez for the observations of the orbits around Sagittarius A star, our supermassive black hole in our Milky Way. And essentially it was this, essentially what they, they didn't quite say black holes. I mean, that's what they implied. But it's consistent with black holes. But really what this is evidence for is ultra compact dark objects that are difficult to explain if they weren't black holes. But like with these things, we don't actually see anything about space-time. It's really the matter dynamics around it. So if you will, like what we knew about strong field gravity from the 60s and 70s was kind of confirmed over years of observations. But like, what about the dynamics? What about this radiative sector? Well, we had the weak field description, but what about strong field dynamics? And that all changed 10 years ago when LIGO detected the first waveforms from merging black holes. And I think now we're starting to, in the last 10 years, we've started to gather evidence about the dynamics of strong field gravity, and it does appear to be consistent with this picture that I showed. Now, one thing that, actually it follows from partly follows from what I mentioned about the quadrupole formula. So, okay, if there were, these objects that were dark compact objects, well, why couldn't we see gravitational waves from them before? Why do we have to look for binary black holes that collide? Well, one is that isolated black holes don't produce radiation. They're very quiet. They're just sitting there doing nothing. So to see actual space dynamics coming from strong field gravity, the region around horizons, we pretty much have to look at black hole collisions. And so this was the first detection that LIGO did. And it surprised a lot of people that that these were so massive that you could actually see them in the spectrum, for the time series of the spectrogram without sophisticated signal analysis. And this is an event that they published a few weeks ago. This was a signal to noise 25 event, which was astonishing for the first detection. And this is a signal to noise 80. And it's actually the little gray lines that you can barely see. That's the actual minimally filtered data from the LIGO detector. So you can actually see the signal. And this is, again, we can never prove that black holes exist. I mean, science doesn't work that way. But the stronger the signal is, and so far there's no inconsistency between the predictions of relativity of merging black holes and this. These are just like direct evidence as we can get about the dynamical strong field nature of GR, and it's a pretty strong consistency check right now. So, if you will, the golden age and then the observational campaign, that told us a lot about the dynamic, about static black holes. We knew about perturbations of them. The last 2 decades has sort of been perhaps we can eventually call this a second golden age, where you finally understood the dynamics of black holes that produced sort of these templates that then LIGO could discover, together with this observational campaign of actually observing the universe in gravitational waves. And that's just begun. I think that this is a very exciting area of gravitational physics, and I think it's going to be exciting. And together with other things like the Event Horizon Telescope and pulsar timing, perhaps eventually they'll see cosmic CMB polarization modes from gravitational waves. So we're just in the early innings of what we might learn about the universe through gravitational waves and strong field gravity. And so I'm not going to say anything more about that, because I hope you've heard talks from LIGO, or if you don't, you'll see more talks from LIGO and EHT that will discuss this. So, so like I've got perhaps 10, 15 minutes left. So hopefully I've set the stage now describing like all the interesting things we know about black holes. And these are a very rough sketch. But at least theoretically, well, what don't we know? So is it theoretically a solved problem? And now it's just about the astrophysics of observing the universe? And yet, in many respects, yes. But there are still a couple of sort of regimes of classical relativity where we actually don't know what's going on, even qualitatively. And just to qualify that, to say if I say we know things, it's at the level of rigor of a physicist, not a mathematician. So mathematicians they tell me that they're close to proving the nonlinear stability of the Kerr solution. So they're not even close to looking at, say, binary dynamics. But when they say prove, they really mean prove. But I'm saying, like, okay, let's just take a physicist level. Yeah, they seem stable. We don't worry. But even from the level of a physicist, like, what don't we know? And there are several things. Like one that I'll then spend the rest of the talk explaining is the nonlinear perturbations of near extreme or Kerr black holes. The generic outcome of ultrarelativistic collisions. So in nature, black holes they if you will, rest mass dominated. They bound systems, they spiral in, even though they get close to the speed of light, 30, 40% before they collide. There's another complete limit where you can imagine shooting two black holes together at near the speed of light. That's actually relevant for, particle collisions above the Planck scale. So then some of you might remember 10, 15 years ago, there were suggestions that the LHC might form black holes. And it's really based on some conjectures of what happens during classical gravity. So again, I probably won't have time to say anything about that, but ask me if you want. And of course, another thing which we'll unfortunately never get any observational confirmation of, well, I shouldn't ever say never, but we also don't really understand the interior structure of black holes. The exterior is very simple. It settles down to a Kerr solution, but we don't understand the interior. Okay, so the last few minutes of my talk, I'll explain, I'll speculate on what might happen for nonlinear perturbations of near extremal Kerr. But let me first then in words say, what is an extremal Kerr? What is a near extremal Kerr? So one interesting thing about the Kerr family of solutions, so these are rotating black holes, so they have a mass and a spin. But let's say in properly normalized units, it's only up to a spin of A. We usually use parameter A for the spin parameter of 1, where there are black hole solutions. If A is larger than that, so if they're spinning faster than some limit, they're not black hole solutions anymore. They're naked singularities. So if you take cosmic censorship, and it's a conjecture, if that really is what happens in the universe, that there are no naked singularities. So the singularities that occur in general relativity are always hidden behind horizons. That means that black holes in relativity can only spin so fast. And the ones that are exactly at that limit are called extremal black holes. And ones that are close to that limit we call near extremal. And the interesting things that might happen, it's a very nonlinear function of A, like when you might expect this to happen. So like what is going to be high spins? It might be 4 nines, like 0.999. Then you get into this regime where you might start seeing bizarre effects. So unfortunately, that means it might not be relevant for astrophysics. To somehow nature would have to create very, very rapidly spinning black holes. If it can create stellar mass black holes that are rapidly spinning, it's not going to be that interesting for LIGO, because some of these nonlinear effects, you need to see that black hole perturbed. The binary motion, even if there were extremal stellar mass black holes that LIGO could see, this doesn't excite any of that dynamics. It's when they collide, then you get excited Kerr black hole. But a collision of two extremal black holes produces a sub-extremal black hole at 0.97, which is way too far away from this. Okay, so so we know linearly what happens with perturbations of extremal and near extremal black holes. So what do we know about that hints that something interesting might happen? And it's like, yeah, we don't have any numerical simulations or perturbative calculations beyond linear that can actually address this question. So it's a very difficult problem. And people can ask me why it's so difficult, but yeah, so the largest simulation that I'm aware of actually perturbing it in full nonlinearity has gone to 2 nines. I'll show you one example of that. So why do we think something interesting might happen? Well, there's several reasons, but the two that I'll focus on here is related to one is the quasi-normal mode perturbations of a black hole. So if you perturb a black hole, it quickly sheds its hair, it becomes bald, if you will, it approaches the Kerr solution exponentially fast in this process called quasi-normal ring down. So it's like you hit a bell, it rings down. That's a ring down. I mean, you can hear a bell because it's got a very high quality factor. Kerr black holes are very, very bad bells. It's almost like, it's more like a bell made of plastic. Like you hit it, it's very, very quickly rings down. So it's very efficient at ringing down, except in the extremal limit. So the least damped family of quasi-normal black holes there's a family of them where the damping time goes to 0 in the extremal limit. So in the extremal limit, they actually do become very good bells. They can ring for a very, very long time if you hit them. But there's another interesting phenomena with Kerr black holes. So they're rotating black holes. So you imagine a scattering problem. So you scatter a gravitational wave, and gravitational waves can carry angular momentum. So you give them like an azimuthal number in spherical harmonics. So you give them an M number. And based on that, they've got a rotational velocity. So the superradiant phenomenon, from this perspective, it's not unexpected, it's not unusual. So if a black hole is rotating very fast relative to the angular velocity of the wave, as it comes in, it can actually gain rotational energy from the space-time, and it can get scattered off with larger energy than it had. So you can scatter a gravitational wave off a black hole, and you can extract rotational energy from the black hole. So nothing is coming out of the black hole. You're not violating causality. You're just taking energy of the spinning space-time and powering the gravitational wave. You must think like if you have a spinning wheel and you throw a little pebble on it, you can imagine it can fly off. Because if you throw it with this pebble, it's not going very fast. The wheel is spinning, and as it hits, it can gain energy. And that's kind of what's happening here with the superradiance phenomenon, but it's happening with space-time and gravitational waves. But the interesting thing is for Kerr black holes, the frequency that marks the onset of superradiance. So that's at the point where the onset of superradiance is it's completely balanced. You throw in a certain amount of energy, you get it back. So from the linear perspective, it's almost like the black hole's a perfect mirror at the onset of superradiance. And at the onset of superradiance, in the extremal limit, the frequency becomes commensurate with the least damped quasi-normal mode. So there's at least one thing, it seems like there's a resonance condition that might happen. But what do you think? Well, okay, what might happen if you've got these long-lived modes, and because it's effectively a reflector to linear order, you've cut off one channel of energy loss of like the perturbation around the horizon, and that at least the speculation is that this is a condition that is good for perhaps some strong turbulent dynamics to form around the horizon. And so, for a nonlinear theory like this, like, let me just say, like, you always expect some form of nonlinearity in terms of mode coupling. So you have a certain mode that's interacting, you're going to have daughter modes, etc., produced, and you can just call that weak turbulence. It's difficult to describe turbulence, like even in fluid mechanics, like what it exactly means. But what I mean by strong turbulence is like in a fluid system, or if you see all these whirls happening in clouds or smoke or something, you know turbulence when you see it. And what it effectively means is that this nonlinear reaction, there's a very efficient energy transfer on a relevant time scale. So usually with Kerr black holes, there is no generic sub-extremal Kerr black holes. You always get weak turbulence because the decay is just too fast. There's not time for these modes to sit around and do nonlinear interesting things. They decay. But if you can get the waves to sit for a long time, then there's a chance that you can get some interesting nonlinear dynamics. And then, like, one bit of energy loss you can avoid is waves are being radiated to the outside. But at this limit where the onset of superradiance happens, you're shutting off one channel of energy loss. So people have conjectured this. And there's some evidence also that this might not be as far-fetched as it seemed. Like if you'd asked a relativist like me, 20 years ago, can gravitational waves exhibit like turbulence, like what you see in a fluid? I'd say, no, that's absurd, because it's a nonlinear system, but it's very different from hydrodynamics. So you don't expect like shocks to form or things like that. But since then, like this ADS-CFT correspondence revolution happened in string theory, and okay, regardless of whether that's a description of nature in any sense, it's a very powerful thing came from that. Is it said that in certain cases, you can make a one-to-one correspondence between Einstein gravity in an anti-de Sitter space-time, and a conformal field theory that lives on the boundary. And that conformal field theory on the boundary does have thermal states, and those thermal states do have a hydrodynamics description. And when the boundary is in a thermal state, it's deal to a black hole in the interior. And so then people said, well, if that's the case, well, at least asymptotically ADS spacetimes, there should be turbulence on the horizons of those black holes. And people indeed did found that. So this is a result by Adams, Chesler, and New. And this is taking a black brane. So in our space-time, 4 dimensions, asymptotically flat, you can only have spherical topology black holes, the curve family. But in anti-de Sitter space-time, you can also have black brane solutions other than that. And so this is like a black brane solution. So it's a black hole with a planar boundary. And so this is a representation of the perturbation. I won't explain the details, but just to show you like what happens when they perturb this. It actually is decaying, but they scaled out the overall decay. But you see what happens with this perturbation, and just by eye, you can see this is what turbulence looks like. So on the horizon of these ADS black holes described by pure Einstein gravity, you get turbulent dynamics. And so people try to compute an effective Reynolds number for a Kerr black hole. And that is okay, it's very sketchy, it's hand wavy, but it's that paper by Louis Lehner and collaborators, this one that I mentioned there, which argued that the effective Reynolds number of a Kerr black hole, to start seeing turbulence, you need 4 nines or higher. So again, we don't know, but it might be that when you get to near extremal black holes with such high spins, you might start to see turbulent dynamics on the horizon. So yeah, and yeah, the last thing I want to mention about this, the other bit of interesting evidence that there might be something interesting going on in this regime came from this case that I mentioned. So in terms of perturbations of Kerr black holes, as far as I'm aware, the record is still what was done by these 2 students of mine about 10 years ago, Will East and Fethy. I can't pronounce his last name, sorry. Will and Fethy. And so actually at the time, we were just more interested in just understanding the nonlinear aspects of superradiance. So the superradiance phenomena, again, that was derived at the linear level. And we wanted to see, okay, well, what happens at the nonlinear level? So now we're going to do the scattering experiment for a spinning black hole. And we want to see how much energy we can extract, but we want to have a huge perturbation coming. So in this case, like the waves, was like up to 10% of the mass of the space-time is in the gravitational wave. And so the results associated with that. But the one thing I wanted to show is like the interesting thing that we didn't quite anticipate, but this goes back to these commensurate frequencies where certain resonances might happen. Let me just first show you an animation. So that's the apparent horizon. So that's something we can locally compute in these simulations. It's a proxy for the event horizon of the Kerr black hole. You can see it's a little bit distorted because the black hole is rotating, but when they're out without a perturbation, it's axisymmetric. And you'll see, so what we're going to do, like the wave is going to come in, the ingoing wave isn't going to be in blue, there's going to be some interaction, and the outgoing wave is going to be in red. So when the incoming wave comes in, it perturbs the horizon, and then it will look like the thing starts to rotate, but that's just because it's distorted it, and it's not axisymmetric anymore, so you can see the rotation. But even before then, it is rotating. So if you like look carefully at that little peppermint shape horizon. So there the wave comes in, it perturbs it, and now you can visibly see the rotation there, but that's just because it's been perturbed. There's an interaction, and now the red is the outgoing waves. I think this was a super radiant case, and so you can't see it from the color scales, but this was a case where the wave had more energy going out than coming in. Okay, but the surprise was as follows. So let me just explain this curve. Okay, a lot of information here. So this is as a function of time, looking at properties of the black hole. So its mass, its angular momentum, and this is something called its irreducible mass, which, if you will, is the area of the horizon. So in general relativity, there's Hawking's area theorem. So the area always has to increase. And so the 3 different curves are, one is a case where the frequency is such that we expect subradiance. So it's going faster than the black hole. So it actually absorbs energy into the black hole. This is the case where we tune it to the maximum superradiance. But this is one where it's at the onset of superradiance. And here is, this is not so close to maximal that it's also at the least damn quasi-normal mode frequency, but they're within 10% of each other. So this is the case where I said, well, in some sense, it's acting like a reflector for linear theory. So nothing is getting in. Okay, but first, let's look at the subradiant case. Yes, the wave comes in, the black hole mass increases, the area increases, and its spin increases. So it absorbed a lot of it. It absorbed most of the wave. The superradiant case, yeah, so the mass decreased, the spin decreased, and the area increased, and sort of ignore that. That's numerical issues. So when in this region where it's interacting so strongly, our apparent horizon find that problems, that was failing. So this is points where we sort of lost track of the apparent horizon. We got an approximate one, but this is not inconsistent with the area theorem. It's just challenging numerics. And this also prevented us from going to larger amplitudes, because for larger amplitudes, we just lose the apparent horizon. And when we lose the apparent horizon, the code crashes. But so area theorem is always increases. But then this onset of superradiance as well, this is sort of intuitive, right? This is supposed to be a case where it's like a perfect reflector to linear order. So non-linearly, okay, it's not going to be a perfect reflector, but it should be bracketing these cases. So it's the mildest changes in the properties of the black hole relative to the superradiant case where we extracted spin and energy, and the subradiant case. But now let's look at the actual geometry of the horizon, like what's actually happening to this perturbed black hole. And the largest perturbations we get at that onset of superradiance. So first, if we look at two measures of what's happening to the geometry, one is to take the ratio of the proper circumference to the polar circumference. We see these very large oscillations develop. And also, if we look at a curvature scalar on the horizon, we get a very large curvature induced by this case. And remember, this red case is the case where, as measured by these properties of the black hole, its mass and spin and area, that was the mildest case. That's the onset of superradiance. So we cited these very large disturbances at that onset of superradiance. And so the guess, like, okay, what might happen if we could actually get very, very close to extremality? This might be a case where we can actually break a black hole, like the hypothetical opera singer that can shatter a glass by singing at the resonant frequency. Now, black holes have resonant frequencies, but because they're so damped, if we'd have to go to very close to extremal to perhaps be able to excite arbitrarily large waves on the horizon, and that might produce a naked singularity. Perhaps, I don't know, but at least this is hinting that not only could we have interesting turbulent type dynamics, but this onset of superradiance, there might be some kind of a zero mode where they're on the verge of being unstable. And incidentally, just to show also, this was a spin of 0.99. I said 1 was the maximum, but like how far are we away from extremal relative to these properties? For example, here, the ratio of polar to equatorial for an extremal black hole is this dashed line. So this is the 0.99 case, this is the 1 case, and you can see they like 10% apart in this measure of that, and also what this curvature scalar is. So we're quite far away from that. We're not 1% away in terms of this dynamics, we're actually quite far away. So if we could get very interesting strong field dynamics about near extremal black holes, yeah, we need many, many nines as well. Okay, and so as I said, yeah, the ultrarelativistic problem, I would not have time for, but I'll be happy to talk about it. So let me just go to conclusions. So I think, the golden age of relativity, as I hope to explain in the earlier slides, in the 60s and 70s, that really is a foundation of like everything that our modern understanding of black holes sort of came from that. And why it became such an interesting subject then, people took notice of it, is not just because we understood the theory, but it seemed like the universe actually had objects that were consistent with black holes. So we needed it to describe the universe. And now I think perhaps what we're sort of at early stages of perhaps a second golden age, where in the last 20 years, thanks to LIGO and the theory community's efforts to understand the dynamics of black holes, we're now sort of getting into an era we can see that the dynamical strong field regime is relevant in our universe, through black hole collisions. And it's also a very interesting thing theoretically. So if you say, like, what is a black hole? It's not just a point particle. It's a structure with an event horizon that's got very interesting dynamics when you perturb it. It's got very interesting collisional dynamics. What happens when 2 point particles approach each other? Well, black holes, they fuse together. They can do interesting things. So, like, all the richness of what a black hole is in relativity is, you need to understand the dynamics. And even though we know a tremendous amount, at least one of the examples that I showed, there's still a shred of parameter space, at least even for stationary black holes, we don't understand even qualitatively. So what I said about possible turbulent dynamics and perhaps breaking a black hole apart, that's just complete speculation on my part. So we don't really know what happens if we crank it up. But I think there's some very interesting things that might be revealed if we can understand that theoretically. You say, just like, how relevant is that astrophysically? And unfortunately, it might not be. So again, as I mentioned, it's not going to be relevant for LIGO, because even if we had two extremal black holes that collided, they form at best a 0.97 if it's comparable mass. The way that we might get lucky, so we want to see the dynamics of a perturbed black hole. So we want to see something where we don't significantly change its mass or spin, but we excite the modes. And one possible hope are supermassive black holes. If there are supermassive black holes, near extremal black holes in the universe, so there must be if there's some mechanism like Sagittarius A star M87, these massive black holes that we see, in the centers of galaxies, if they could be spun up to near extremal, then what LISA could measure is the so-called, what is MRES, the extreme mass ratio in spiral. Then you can have a small black hole, like a 30 solar mass black hole, spiraling into a 10 to the 7, 10 to the 8 solar mass black hole. Such a high mass ratio will not push the black hole very far from extremality when it merges. So if you did have a 0.999 spinning supermassive black hole, we could see possibly turbulent dynamics or the effects of very large curvatures forming near a black hole if there's an MRE. But who knows? We don't know what's out there. I think astrophysicists will say it's unlikely that some astrophysical mechanism can spin black holes that high. So it might in the end just be another interesting theoretical question. But at least it's interesting theoretically. It might be interesting astrophysically. Thank you for your time.